Welcome to LabMinutes.com and our lab video series on MPLS. You can find a complete list of our MPLS video on our website by clicking on the link above and sign up for our newsletters to receive the latest video updates. In this video, we're going to look at how we can use Mpls Ping and Traceroutes to troubleshoot an issue in an MPLS network and why a regular ICMP ping might not be sufficient for that. And we're also going to look at the significance of Mpls MRU, or the maximum receive unit, and how we can address the additional Mpls label that gets added to the packet size, and how we can avoid fragmentation to the Mpls label packets. Now for our lab topology, we're still using the same physical topology as our previous lab, so nothing's changed on that. It's to have 8 routers, R1 through R8, with these routers connected as shown in the diagrams. Now moving down to our lane 3 topology, we already have the MPLS and LDP configuration completed from our previous lab. So currently we have LDP running between R1 through R5 routers with their loopback 0 advertised to the EIGRP, and for the edge devices we also have a complete reachability between their loopback 10 through 12. Now let's start on now task number 1, Mpls Ping and Traceroutes. First, we need to run a Wireshark packet captures on R1 interface FAS00 and then observe a ping from R6 loopback 10 to R7 loopback 10. Okay, so at this point we already have the Wireshark packet capture configured from our previous video when we were looking at the LTP packets right here on R1 FAS00, although back then we didn't quite look at the MPLS packets itself, which you're going to be doing right now. So just to show you on switch 1, let's do show monitor session number 1. And we currently have a source of the span port to be FAS01, which is where our R1 FAS00 is connected to, and then we have a span machine or Wireshark machine connected to our FAS023, okay, which is the computer I'm currently on. So what we're going to do is to bring up our Wireshark and restart the capture, and on R6 we're going to do a quick ping from R7 loopback 10, sourcing from its loopback 10 as well. 10. Right here you can see it's pingable. You can also see some CMP packets right here. Let me stop the capture and take a quick look at the ICMP ping packets that come across as the MPLS packet. So right here, source from 6601, which is R6 loopback 10 going towards 7701. So here we have an Ethernet frame header, followed by our MPLS. And if you look at the Ethernet header, there's a type field that indicates it will be followed by a MPLS label. And then here we have our full bytes MPLS label. And that includes the actual MPLS label. You can see it's label 19, followed by the 3 experimental bits. And then we have a flag for the bottom of the label stack. One being it's the bottom or it's the last label of the stack, and then it ends with the TTL value. Okay, so all these are 4 bytes. You can see it's a group of 8 bits, 4 groups, so 1, 2, 3, and 4. And then after the MPLS header, we have our regular IPv4 header, okay, with the true source and destination IPs. Alright, so that's what a MPLS packet looks like. What we're going to do next is to force traffic to become unlabeled between R4 and R2. So that's going to be between these 2 routers right here. So currently we're starting from R6 and then we're trying to get to R7 loopback 10, and we're just going to force a packet to become unlabeled right here so we can troubleshoot that using our MPLS Ping and Traceroute. So first what we're going to do, since we have 2 equal cost paths right here, so R3 could have picked R5 or R4 at this point. So just to make sure that the traffic will get forced through R4, we're going to shut down this link right here between R5 and R2. Okay, at the same time, we're going to disable our LDP between R2 and R4, okay, which is our task list right here. So let's go ahead and do that. Starting on R2, we're going to shut down, let's see, there will be serial 010, shut. And then on the other serial interface, which is 000 facing R4, we're going to do no MPLS IP to disable LDP. Okay, and just to prove that R4 would no longer send a label packet to R2, we can do show IPsef for the R7 loopback 10 7701. You can see there's no tags or label being imposed onto the packet. Okay, now going back to R6, and we can try to ping that one more time. You can still see it's pingable. And just to prove that the traffic is in fact going through R4, we can do a trace route also. Sourcing from loopback 10, you can see it goes from 1, 3, 4, 2, and 7. Okay, so it's followed this path right here. 1, 3, 4, 2, 7. Okay, and even though the packets becomes unlayable between R4 and R2, the packet can still be correctly routed to R7, and that's because R4 has R7 loopback 10 in its routing table. So I can easily just do an IP lookup on the routing table, and then it will find out that next hop is still R2 without having actually to rely on the MPLS label. But that might not be the case if you run services like MPLS VPN and you have multiple MPLS label, and all the router has a knowledge of is to get from one router to another within the MPLS network, and not so much of the actual source or destination subnet, since that will be carried across MPBGP. Okay, in that case, if the packet become unlabeled within the MPLS network, the router itself, whether it's P or PE router, might not actually have the route to its final destination, its routing table, and at that point the packet will be dropped within the MPLS network. So it's best to make sure that the packet will never become unlabeled within the MPLS cloud. But for what we have here, if you're trying to just do a troubleshooting with the ICMP ping, it would not help identifying issue, because you can see ICMP ping goes through just fine, although the packet has become unlabeled. Okay, so now to troubleshoot this packets becoming unlabeled in the network, what we're going to do next is to identify a problem with the MPLS ping. Okay, and the way that the MPLS ping works, it's going to be initiated on the one label switching router to another, and not so much from the true source and destination. That's not even part of the MPLS, so it has to be done within the MPLS cloud. In this case, we're going to do that or initiate the MPLS ping from R1 to R2, since we know that's going to be our last MPLS enable router before it hits R6. So now I'm going to restart a Wireshark packet capture. And on R1 itself, let me do a quick debug IP ICMP. And now we're going to do a ping, give you a question mark. You see they have an option for MPLS, and then there's to specify there's a different flavor of MPLS ping. The one that we're going to use here is IPv4. You can see there's also option for pseudo-wire or traffic engineering if you happen to troubleshoot an environment that's providing those type of services. Okay, but for us it's just IPv4, and then we have to specify a target FEC with the mask. So in this case, we're going to be targeting R2 loopback 0. And we need a /32 for the mask. And then there's a whole bunch of options that you can do. We'll go through those in a second. But for now, we can go ahead and enter. As you can see that we're getting a multiple dots. Right here, dots means it's a timeout, so it cannot reach the 172.16.02 as our destination here. And that's indicating there's an issue in the network. Let me go back and stop our packet capture and see if we can find what we just did. So right here, the packet is identified as MPLS echo request, so it's not a typical ICMP request. That is being sourced by the R1 fast00, which is 13.2, and you can see the destination is a little strange. It's actually a local address 127.0.0.1, and the reason being that the MPLS ping used then as a destination is if the packets happens to become unlabeled within the MPLS network, it would not continue to be routed using a regular IPv4. I mean, obviously that IP is not routable in the network. So as soon as the packet becomes unlabeled, the router that receives that packet will immediately reply, as you can see right here, which is the case for router R4, with the time to live exceeded. And this is because if you look at the IPv4 header right here, the MPLS echo request, let's see if we can find that, has a time to live of 1. Okay, that's another thing that the MPLS ping does to the packet itself, because once the packet becomes unlabeled, then the packets will pretty much expire with the TTL. So let's go through the packet real quick with the Ethernet frame right here, and then we will have our MPLS header that's incoming to R4 in this case, and it has label 29. So all that is good. We already talked about the source and destination IP, the destination being the local address. Okay, and then we also pointed out that the time to live of the packet itself is 1. Let me go back and show you the time to live of the actual MPLS header is actually 255. Okay, so packet only becomes expired when it becomes unlabeled. And we also have right here a don't fragment bit set on the IP header. Okay, and after the IP header is actually a UDP header, so this is not a typical, again, ICMP packet. It's actually a UDP, and the Mpls Ping also uses a well-known port 3503, and it's on Wireshark label as LSP Ping. Okay, and the content contains MPLS echo, and the content of that has some additional information that you can potentially set as part of your ping MPLS command. For example, the reply mode right here by default, the reply of the MPLS echo request is going to be in the form of IPv4 and actually not a MPLS packet. As we can see right here with the ICMP time to live exceeded, it doesn't really contain the MPLS label in the header, and this is because we want to make sure that we isolate the directions of the traffic and make sure that the return path doesn't become doesn't influence whether or not the return packets will make it back to the originator of the ping. Okay, so by using the reply packet to be an IPv4 regular packet, we almost guarantee that the packet will be routed back successfully. Now you can see it's a regular ICMP time to live exceeded with a time to live on the IP header of 254, and then the actual content of the MPLS request content as part of the ICMP payload. Okay, so let me restart the packet capture, and then we can try to do another ping. But this time we can look at the various options that we have. We can set a different destination if you like what we saw in the packet capture. The default destination is 127.0.0.1, but you can identify to pretty much whatever you want in the header, although there's usually no need to do that. We can set a experimental bit to something that you like. Let's, for example, do an EXP of 5. Okay, and we can do for example, a repeat count or reply mode. What we saw again in the packet capture, the default reply mode is a regular IPv4, but you can also force it to contain a router alert on the reply packet. And what that does is once the packet has been tagged with the router alert option, the packet will be forced to be software processed along the way, so that basically bypass any potential hardware or line card inconsistency. And that's again for the reply packet, and just to increase the probability that the reply packet will make it back to our router. Okay, so we're going to set the mode router alert, and then we have sweep timeout. Timeout is just the regular time that the router wait for the packet to come back. We'll leave it at default. We can adjust the TTL if you like. So as we saw, by default the TTL was 255. But let's say we want to set that 250, and just to see how that show up on our packet capture. And then go ahead and enter. And we can still see it's still timing out since we still have that unlabeled packet issue. But if we look at the, again, MPLS echo request, starting with the MPLS label, you can see now we have the experimental bit set to 5, as we set that as part of our command options. And then for the TTL, MPLS TTL is now lower to 250, and I believe the other modification that we made was the reply mode right here. Instead of a IPv4, IPv6 reply, now we have added the router alert option into that as well. Alright, so as you can see that we did the debug ICMP on the router R1, and we've been receiving a time exceeded from 34.4, which is router R4, so we can kind of tell that there's an issue going on at the router R4, and that will be where you start your troubleshooting at. But let me also show you how to use a traceroute to track the issue down, and that's also our next task right here, identify problem using MPLS traceroutes. So now on R1, actually let me restart the capture one more time, and then on R1 we can do a traceroute and then option MPLS. Okay, same thing, we still have two advanced options of multipath and traffic engineering. I think the other one was the pseudo-wired for the ping, but here we're going to use IPv4. And then our target is 0.2/32, and then enter. Okay, so you can see that the first hop, as the packet leaves the router R1, that is okay. Actually, let me kind of kill that. Let me stop the capture as well. And we know that the packet is coming from 13.1. Look at that, the packet capture. Alright, so the first hop leaving router R1, it has label of 29. Okay, and then once it hits the router R3, you can see that it's still labeled as indicated by the L, letter L in the front, and L translates to label output interface. So we're still good at that point. But once it hits the router R4, all of these kind of goes away, and then you can see that it gets stuck at router R4. As we now keep getting, again, back the time exceeded from R4. So now this kind of reassures that there's a definitely issue at the router R4. Now let's go over to our packet captures, and let's do IP address filter based on the source IP. Go apply, or the actual edge IP in general, 13.1. Okay, so the way that the traceroute or MPLS traceroute works is still using the actual MPLS echo request, just like the MPLS ping that we saw, with the main difference of the MPLS TTL that it actually starts with TTL of 1, so it definitely expired at the first hop. But since we didn't have any issues in our first hop, you can see that we get a MPLS echo reply from R3. Okay, and then it follows with another MPLS echo request, but this time with the TTL of 2, so that would be 2 hops away. And by that time, the packet will basically reach R4, so that will be your first hop right here, no problem. And then once it hits R4, the packets become unlabeled, and this is where we start again getting the ICMP time to live exceeded packet coming back from R4. And then after that, I can see the TTL keeps increasing. Here's TTL of 3, and then we have TTL of 4, TTL of 5, so on and so forth. But as you can see, the packet never make it past R4. Okay, since that's where the packet becomes unlabeled. And all of these packets, as far as the requests, of course, they are a UDP packet and not ICMP. Okay, and before we move on, let's try a quick ping MPLS to the actual destination in this case, which is 7700/24. Now you can see that doesn't really work since we're getting the same thing coming back from R4. And just to reiterate, the destination of this is the FEC, which is the route of the prefix itself, not so much of the IP of the destination. Okay, because it's how the router look up and figure out what label to use for the outgoing packet. Same thing with traceroute. So instead of ping, if you do trace MPLS IPv4, you can see that we are getting the exact same result as what we saw earlier. And you can only use the true destination FEC only when you don't run like services like MPLS VPN, because the cloud would not have or have any kind of knowledge of the true destination. And in that case, you have to go back to what we did earlier and do based on the traceroute ICMP to the loopback interface of the egress router, okay, instead of the true destination. Okay, now let's go ahead and re-enable LDP on the link between R2 and R4 that we disabled, just to put kind of things back. So MPLS, this is actually R1. We hop over to 2. Right here, no MPLS IP. And just to go back and show you that things should be recovered already. On R1, if you do a ping to 172.16.0.2/32, you can see all of our 5 pings came back successfully. And let's try what happened if you do the pings to the 7700. And you can see that since R2 is not where the network 7700 is located, the packet becomes unlabeled after that. That's why you get a return of B, and B translates to unlabeled output interface. All right, so that should complete our task number 1.